So I realize my mute might be on. You might not have heard any of that. So I'm going to repeat all that. So I apologize to anyone who missed any of that, and we'll make sure when we load this up on YouTube for review that is chopped off. So we're welcome to the demonstration corner. We're going to talk about the use of the transient plane source method on the MPV and the GHFM-01 for measuring carbon fiber, graphite carbon fiber, both in the MTPS sensor for measuring single-sided with an absolute sensor, as well as symmetric on the TPS sensor, so on the MPV. Now, everything we talk about and discuss in terms of the use of the transient plane source method with the MPV, of course, that theory and the assumptions of that method are true for the transient plane source method that's available in the MP1. So before we get into that, let's talk, as tradition, we'll turn around again and I'll make this quick because now this video is going to run a little long. Our THWL1 is for measuring liquids and phase change materials according to ASTM 7896, thermal conductivity, thermal diffusivity, and specific heat, an overall temperature range of -160 to 300 Celsius with a back pressure up to 35 bar if you need that. There's different ranges within that. Our small format ASTM C518 for measuring small format insulation, specifically designed to be able to test small format insulation according to ASTM C518. The big advantage is this would be the smallest heat flow meter on the market. Our MP2, which is the baby measurement platform system, it would be our economic, what we call portable, combining primary sensors for thermal conductivity of solids by transient plane source sensor, thermal conductivity of liquids by transient hot wire sensor, and thermal conductivity of soil and polymers by transient line source sensor. So we have lots of demonstration videos on all of these. So MP1 is the industry leader in thermal conductivity platform for transient methods. This combines several features that make the controller unique. So when I say the controller, this would be the controller box. These are temperature platforms that you can add to it based off of the method you want to use for your analysis. So the MP1 as it stands, you have a front channel, so 1 in the front and 3 in the back. 3 in the back, which enables you to connect up to 4 devices or temperature platforms or sensors. And combined with the smart software that we have, it lets you take advantage of each channel and organize and schedule sensors and temperatures to maximize the volume. So essentially, an MP1 with 4 channels is equal to having 4 instruments side by side, but obviously much more economical. So this method, rather the MP1, measurement platform 1, combines transient plane source from 0.005 up to 2000 watts per Kelvin. This is the temperature platform that's available. Again, we have lots of demonstration videos on this temperature platform. Proprietary device that you can add as your needs grow. This one as it stands is 0 to 300 Celsius, fully optimized to make high quality transient plane source measurements over rapid stabilization of temperature. There's available expansion from -160 to 300 Celsius. This is the transient hot wire following the same standard as the THWL1. This as it stands is 10 degrees to 200 and up to 20 bar. This can be expanded. -160 up to 300 Celsius and 35 bars. So there's a lot of expandability. The other methods that are not shown here that are available on this are transient hot strip for measuring anisotropy in elongated materials. So basically a different shape of material, trying to get in that third direction on materials that are more rectangular shape. And transient line source following ASTM D5334 and 5930 for measuring soil and polymer. So there's lots of demonstration videos on the MP1 because we put a lot of work into this to make sure it's the leader. And then our GHFM-01, which follows ASTM E1530. We'll be talking a little bit more about this today, so I won't spend a lot of time, but the overall temperature range of the plates is -20 to 310 Celsius. It does measure thermal resistance, so it's one of the steady state methods. It measures thermal resistance, which is its main advantages are for measuring heterogeneous materials from 0.1 to 100 watts per Kelvin or non-repeating layers. And we'll be describing why that's important, and if those types of materials are what you want to measure and you're using a transient plane source method, you might be generating erroneous data, and we'll talk about that, what that means. This is the other steady state method we have, which is a heat flow meter. HFM-100 stands for the thickness. This size is 300 by 300 by up to 100 millimeters thick. And there is an HFM-50, which is 200 millimeters by 200 millimeters and up to 50 millimeters. And this is designed for measuring insulation and construction type materials. It can be extended range up to 2.5 watts per Kelvin with the high TC kit. And there's also a specific heat module so that you can measure direct specific heat of your building or insulation materials. The basic temperature range that's available on those two models I mentioned is plate temperatures of -20 to 75 Celsius. There is a high temperature version which is -30 to 110 Celsius. So we invite you to learn more about the HFM-100. So what we're going to talk about today is the measurement of fiberglass and by the transient plane source method on the MPV. Of course, again, as I mentioned, the theory of measuring anisotropic samples is the same on both the MP1 and the MPV for measuring such materials. So these are just acquired off-the-shelf fiberglass materials. If I hold it right in the right color, you can certainly see the fiberglass. If you could see the cross-section of this, you would see these are highly repeating. So these are layers of the carbon fiber layered on top of each other, so highly repeating through the thickness. So what I mean by that is as the heat diffuses through the thickness direction, it's diffusing at the same rate. So the theory, and why I keep repeating that, the theory of the anisotropic approach with the transient plane source is that your sample is, if it's a layered material or whether it's like this layered as one solid or layers of materials that are freestanding on top of each other, if it's not repeating, you introduce errors into that assumption. And there's, when you make those measurements, you can create and see errors. And there's a way to investigate that, and I'll show you how. But that is one of the main assumptions of the anisotropic approach with transient plane source, is that it's homogeneous and that through the thickness, the organization of the anisotropy is well organized, and the layering or anisotropy through the thickness is repeating. So for setup of this sample rather, to the two sensors that we have available on the MPV, which is if you want to come in, the two sensors that we have available are the MTPS, which is our modified transient plane source, absolute version of it. We did a demonstration the other day showing how it's constructed to follow ideal theory of transient plane source, therefore not needing any contact agent between the sensor and sample, and still having all the strength of an absolute method such as variable test time, which is what you'll see how important that is to making anisotropic samples. We'll demonstrate that with data, and the ability to vary power. So those are the key advantages of remaining with a method that's absolute. What does absolute mean? It means from the output of the raw data of the instrument, the thermophysical properties are directly calculated with no offset calibrations or factory calibrations, because we're following the ideal theory. So for use of the MTPS sensor when testing material like this, we call that asymmetric or single-sided setup. It can be done with a weight, or you can introduce something just to protect the surface of the sample. Of course, this is the active test area. The diameter of the sensor that's sitting dead center is 12.8 millimeters. This is the cradle that sensor can fit into, which allows you to apply pressure with this device. So we can set that up. We can do that with a weight, or as this material is not compressible, we can just apply thumb tight, and that's a good setup for asymmetric or single-sided test using the anisotropic approach. If it was a bulk sample, it would be the exact same approach, meaning three-dimensional. And out of the anisotropic test, we'll get axial values, so through thickness, thermal conductivity and diffusivity, and in plane thermal conductivity and thermal diffusivity. So that's the asymmetric setup. So now we'll show you the symmetric setup. Again, with the MPV, included is the transient plane source sample holder, as well as 3 diameters of TPS sensors. Those really give you a lot of ability to measure variances of size and thermal conductivity range. These 3 different diameters, they really do cover a lot of the applications associated. Depending on whether or not you are measuring low to middle conductivity or high conductivity, the basic thermal conductivity range on the MPV for transient plane source is up to 100 watts per Kelvin. You can add a max package, which takes that up to 500 watts per Kelvin. So it just depends on your samples, whether you need that max package. In addition to the transient plane source method on the MPV is our transient hot wire. So for measuring ambient, thermal conductivity, diffusivity, and specific heat of liquids and PCMs. And there's an upgrade to this sensor as well if you want to measure with pressure. The upgrade you can make to this adapter to go up to 300C is just a peak version of it. So we're going to set up a sensor in the quick attach adapter. So it's a little awkward. Hopefully you can get the idea. So there's 4 contact points. We're setting the 4 contact points in the downward direction to make the electrical contact with the sensor. And we just tighten those down uniformly. And then we're going to introduce, again, symmetric test. We're going to introduce the sample on the bottom. And we can lower the sensor to accommodate the change in thickness of the bottom sample. And just tighten that. So here we have our bottom sample, and we can introduce our top. And lower this for macro change, and then for micro change, we just spin that. You have a permanent, or rather an affixed symmetric setup for measuring graphite, or rather carbon fiberglass. And that's the demonstration of the 2 setup configurations. Now we're going to talk a little bit more about the GHFM and why that method is still very critical. For this material, you could say it's less critical, but for variations of it, it is more critical. So coming over here, this is our GHFM following ASTM E1530. Again, we're going to, what happens when we set a sample up in here, the 2 plates come together at a specific pressure or thickness, depending on if the material is compressible or not. That's all controllable through the software. In our case, if we were to measure the graphite, the carbon graphite by itself, the carbon fiber, I should say, by itself, if this is a repeating layers through the thickness, you would expect the thermal resistance or the thermal conductivity calculated from this measurement, which is highly one-dimensional. So what makes it high confidence and highly one-dimensional is you have 2 plates come together covering the full area of that sample and a guard oven closing in on it. So what happens when you make a measurement, we typically have a 20-degree delta on each side. So for example, if the top is 30 Celsius and the bottom is 10 Celsius, we have a mean of 20 degrees. Our guard would be at 20 degrees. Of course, a better example would be if we had a mean of 50 degrees, our oven would be set to 50 degrees, and we'd have a 10 degrees above on the top and 10 degrees below on the bottom. So there's 2 plates that come together, and we'll show that. But before I do, that value you would expect to correlate well with the transient plane source. If the ideal theory is, rather the assumptions from that method is organized thickness and repeating, and this method's measuring a full thickness, the thermal conductivity should be the same, the axial value for that. And we have data to demonstrate that. Well, if we add a layer to this structure, so here's a thin piece of Pyrex, so it's just to demonstrate if we add a layer of Pyrex or something like steel, and we repeat that measurement with transient plane source, you will get a result. But the result will be some average between heat spread radially through the added layer. So I'm describing the effects of non-repeating layers. You'll have heat spreading across the added layer that we introduce. Whatever's closest to the sensor will dominate that air, that source of air. And there'll be a certain amount of heat that penetrates through and into the, in this case, the carbon fiber. What that does is that breaks the assumption that we have a repeating thickness. the layering is repeating and highly organized. And your results will be not very useful depending on the degree of non-repeatingness. So here we have a large piece of steel at about 13.5 watts per Kelvin with a carbon fiber that is 1/2 inch thick. The effect of that through the thickness is going to change. You have two resistances coming together, and the in-plane value would be parallel resistances. When you're measuring transient plane source data, the effect of that will be dramatic. Much more dramatic than this one, which is Pyrex, which has about a 1.1 watt per meter Kelvin. So the effects of each will affect the assumptions made by the transient plane source and generate erroneous data. But when you're measuring this with guarded heat flow meter, the guarded heat flow meter is going to see this as a resistance through the thickness, see this as an added resistance, and creates one new resistance. Or the steel, it's going to see this as a resistance, and it's going to see the added steel as an added resistance and give you one number, high confidence. And even though the steel is, it could potentially have heat loss before the heat penetrates all the way through, with the guard sitting at the mean temperature between the two plates, you have most of the delta across the thickness. So when you're looking at the heat, if you were able to see this and look at the heat penetration through this material between the two plates, you would see the effects of the dominant amount of heat being forced through the thickness, because the mean temperature around it is sitting at the mean temperature. That guard is forcing the mean temperature to stay at the average temperature. So it's really creating this one-dimensional delta and promoting one-dimensional heat travel through that thickness. So, and then heterogeneity, we don't have any data to show necessarily on this sample, at least in this demonstration, but this is a rather extreme example of why this method is ideal for such materials like this, because this is heterogeneous. This is a cement core with large aggregate in it. The aggregate could be 2 or 3 watts per meter Kelvin, where the concrete or cement is half a watt per meter Kelvin. And if you were to test this with transient plane source, you can certainly maximize it with big sensors and long test times, but for a high confidence value, resistance across the whole thickness, giving you one number with no effects of individual thermal conductivities influencing that transient is pretty critical. So the guarded heat flow meter still has a very important part to play in characterization of thermal resistance and thermal conductivity, especially for materials between 0.1 and 100 watts per meter Kelvin that are complex in nature. So composites that are not repeating through the thickness or heterogeneous. So I'm going to share the desktop and just review briefly the data we generated on the TPS method for the carbon fiber, and then with the introduction of the Pyrex and steel layer on the GHFM, just to give you that data. And this is from a webinar, and in the description of this video we'll have a link to this webinar, which does a full layout of the description of the experiment and the setup of the experiments, demonstrating why this is important. So this is transient plane source data, as well as GHFM and LFA. You can see out of one measurement with the TPS method, we get thermal through plane thermal diffusivity and thermal conductivity, and in plane thermal diffusivity and thermal conductivity. And of course, that material is layered in such a way that it has a higher in plane thermal conductivity than through the thickness. The real takeaway from this, in addition to the ability to measure multi-direction, is at different time scales of 5 seconds, 10 seconds, and 20 seconds. So that's the heat penetrating through different amounts of thickness. That's if you were looking at how much penetration with each of these, it's increasing with increased time. And this is a good demonstration that this material is repeating thickness and that the thermal conductivity stays the same through the thickness, because at different time scales you have essentially the same properties. And you have pretty good correlation with guarded heat flow meter. Again, this method is, the guarded heat flow meter is quite ideal for this material, but not as critical as if you add other elements of complexity. So you have good correlation of values. And of course the GHFM only measures through the thickness. It's an isolated or guarded method for measuring resistance through the thickness. If I skip ahead, we can review the GHFM data generated on the same samples with an added piece of Pyrex and steel. And you can see that the Pyrex, which has an intrinsic property of around 1.1 watt per meter Kelvin, it does change the thermal conductivity, and then we add the stainless steel, which has an intrinsic thermal conductivity around 13.5. You can see the effects of that increase in the conductivity. So again, those are individual resistance. You add to them, and the calculation that is being done automatically through this measurement is resistances in series, and of course that behaves the way it should. So you're looking at any laminate stack that is non-repeating. This demonstrates the importance of looking at the full resistance to get a high confidence value. And if you were to measure this with the transient plane source data, rather the transient plane source method, you would have infinitely changing thermal conductivity with time, with change in time scale. It would just keep changing because there's no one number. It just keeps changing with the amount of heat that's diffusing in the one layer and how much heat is diffusing in the other layer in a non-organized manner. So that is a discussion of anisotropy measurements, both with the transient plane source on the MPV, which would be the same theory as the MP1, and the guarded heat flow meter, and why it still plays a rather critical role in measurement of complex materials. I invite you to review this webinar if it's of interest, and please write us if you have any questions. We're happy to answer them, or if you want to discuss your samples between these two methods, we're happy to do so. Thanks so much for your time, and we look forward to the next demonstration.